Okay, so we're now going to be applying the acid-base equilibrium, or just the equilibrium problems, to acid-base chemistry. And so I want to spend some time today really going over what's an acid, what's a base, how they interact with water, with each other, because this is kind of a long section of the course. We cover equilibrium, then we apply equilibrium to acid-base and learn about pH, because again, those are all equilibria inside water solutions. And then we look at the solubility of insoluble things, so precipitates, and we apply equilibrium to that. So there's really three major pieces of equilibrium. So equilibrium in general, which is what we've already covered. Now this section of acid-base chemistry, which gets also into titrations and buffers, and then into precipitates. So we're kind of in the middle of the equilibrium stuff. That's why if you look at the schedule, this is a really long section of the course. That means this test is going to be really tough. So this is typically the most difficult exam. So continue to review the past videos, like from a week ago and so on. So always be studying for this next exam. If you think you're going to sort of spend the last 2 days in this section brushing up on it, it's too much material to do in 2 days. So sort of set aside an extra hour or two each week, to kind of review, study what's ready for the homework, but also review the last homework, and just keep reinforcing that material so that you go into the exam confident, okay? So in terms of acids and bases, the real interesting stuff is with the weak acids and the weak bases. The strong acids and strong bases are just like strong electrolytes. You put them in water and they 100% ionize. So they break apart and produce acid protons, which are scooped up by water to make the hydronium ion and whatever anion we have. And so this perchloric acid would spit off this proton and make the perchlorate anion in water. Hydrochloric acid is going to 100% dissociate into this proton, which will stick on a water molecule and make hydronium ion and chloride ion. So all of these, when we put them in water, the reaction goes to 100%. There's just a very little measurable amount of the HCl in water. It's all dissociated. The same with the hydrobromic acid, hydroiodic acid. Notice it's all the halogens, but not fluorine. Fluorine is a weak acid. So hydrofluoric acid is a weak acid. And the only thing I can think of is just that the fluorine atom is so small that there's more of an equal sharing of the electrons with the hydrogen. So they're comparable size. And so because of that, it holds on to the hydrogen more. The hydrogen has enough pull with its one proton to have more of a covalent bond, less of an ionic bond. But these others, they split apart. Then we have nitric acid, again, a very strong acid. And then sulfuric acid is listed in this table, but it's the first proton only. So we will deal with sulfuric acid in the equilibrium acid-base section, but a lot of times it's just the second proton that we're dealing with. So we'll study that. So memorize these as your strong acids. The strong bases, what do you see as a trend over here? It's not even on, or no? Oh, what'd you say? Yeah, for sure. There's a trend here. The alkali metals, lithium, sodium, potassium. This would also be rubidium and cesium hydroxide. It's just, those are pretty rare elements. And so these are the most common ones. And then the group 2 elements give 2 hydroxides each. So calcium, strontium, and barium. But notice all of these strong bases have hydroxide on them. And so those go right into solution as the basic component. They don't have to really react with water to produce a basic solution, because the acid-base components in water are hydronium ion and hydroxide ion. And these directly produce the hydroxide ion. There's no reaction needed. So they're really strong bases. Now these are in line with the solubility rules. So notice I've shown the solubility rules a couple of times. We're really going to use these rules when we get to precipitates part of the equilibrium, but I just constantly want to put them in front of you, because group 1 cations, lithium, sodium, potassium, rubidium, and cesium, those are going to be soluble. There are no exceptions to getting those, to precipitate out. They stay in solution. And so if I put a hydroxide with any of those, I'm going to have a strong base. Okay. And so these hydroxides are strong bases. If you put OH on any of these, including ammonium hydroxide, so NH4OH. Okay. And the same with these halides. Notice chlorine, bromine, and iodine are sort of set apart from fluoride. Fluoride, when you couple it with a hydrogen, is going to be a weak acid. These right here, the nitrate and chlorate, are going to make strong acids, but and notice there's no exceptions to these being soluble in water. But if you put protons on them, these form strong acids, and these make weak acids. And so there's kind of a split here in terms of these anions. This is the acetate anion, and it makes acetic acid, which is a weak acid. And this is the hydrogen carbonate anion, and it makes carbonic acid. So just again, if you memorize that nitrate and chlorate are strong acids, then you'll be able to tell the difference between these groups here. Now down here we have these insoluble ionic compounds, and so if you put these in solution, they will behave as bases. They will pull protons off of water and make bases, but they're weak bases. If you put protons on them, they'll make weak acids. And then down here at the bottom, obviously the hydroxides. If you have hydroxides with anything that makes them soluble, like the group 1 cations, then they're going to be strong bases. So let's balance the following acid reactions. So here's perchloric acid. I'll just show you an example. In all of these reactions, we put the acid in water. So it's an aqueous solution. And how does it interact with water? So we show that with reacting with liquid water. So this is an important part of the puzzle here. This is liquid water. And it donates that proton. So that proton goes over here and attacks the oxygen and makes hydronium ion. So H3O plus, this is the active species of an acid in water, is this H3O plus. Sometimes in the past, we've just written it as H plus, aqueous. There's really nothing wrong with that, but this is more accurate to write it, the acid reacting with water, making H3O plus. It really reinforces the fact that water is the medium that's adjusting what pH we have and what acid and base concentrations we have. If I take a proton off of this molecule, I'm left with an anion, so the ClO4 or perchlorate anion. So notice it goes from perchloric acid to perchlorate. So that's the anion. And so if you have something that ends in ATE, to go backwards to the acid, you just take that root perchlor and put ic on it. It's perchlorate becomes perchloric acid. Acetate becomes acetic acid. Now let's balance the one for hydrochloric acid. So we have hydrochloric acid reacting with water. We're going to make H3O plus, aqueous, plus the anion, Cl minus. Okay.
Would that still follow the rule that'd be chlorate?
No, whenever you have these binary acids, you have this hydroic, okay? And so that tells you here, hydroic, it just becomes chloride. So okay. This is just a review of the naming sections in the first part of the course. So go back if you're confused or you want to review, go back to the binary naming or inorganic naming chapter in the book, and it's probably chapter 2-ish, okay, where you get into the naming of these things, and it will have rules associated with the naming of acids and their anions. Okay. Nitric acid. So here's a nitric acid. It should make the nitrate anion. So again, we make that acid species, hydronium ion. Okay, so notice the number of protons are acid protons. We get a minus charge. When we take that positive charge away, we're left with a minus charge on the anion. The nice thing about this for equilibrium purposes is when we have a polyprotic acid like sulfuric acid, they react with water one proton at a time. That's really nice, because then we can do a different equilibrium for each proton as it comes off. Each one of those will have its own acid dissociation constant, and we'll look at what that means in a minute. So let's go ahead and write just the first proton comes off. So that first proton goes onto water. And so how do we write that with just one proton missing? We have HSO4 minus. And this one would be called the hydrogen. Yeah. The hydrogen sulfate anion. Okay, just to show that it's got the hydrogen on it. If you just wrote the sulfate anion, that'd be SO4 2 minus. So with all the hydrogens missing. Okay, let's do one more. See, notice how there's a trend. We have acid plus water gives hydronium ion, and then that acid minus its proton. So a lot of times we see this written in generic form. It doesn't matter what the acid is. If you're just showing the one proton equilibrium, we have this generic acid, HA, plus water gives H3O plus aqueous plus A minus. Notice everything's aqueous except the water. So all the aqueous things will show up in the equilibrium constant expression.
So when they dissociate, will the charges always add up to 0?
Yeah, maybe not. There may be a charge. Like if we take this one, let's do this one next. So let's say this behaves like an acid. HSO4 minus plus water. They won't add up to 0, but they'll add up to, they'll equal each other. The left side will equal the right side in terms of the charges. So now we have on the left side a -1, and on the right side a +1, -2. So they both equal -1. Okay, so that's a good question. So that's one way to balance equations. You balance them with the number and types of atoms, and you also balance the charge. Okay, let's look at the hydroxides, the soluble hydroxides. When they dissolve, they directly produce strong hydroxide base. And so if sodium hydroxide dissolves, you just have Na plus and OH minus. There's no reaction with water because these just go right into solution and produce hydroxide. Calcium hydroxide, notice that when this one completely dissolves, we get, well, let's go ahead and balance that one. Okay, what do we get? We have the calcium ion, and we have 2 hydroxides. So if I weigh out enough calcium hydroxide to equal 2 moles, and I put that in a liter of solution and stir it up until it dissolves completely, I have a 4 molar solution of hydroxide, because those 2 moles of calcium hydroxide gave me 2 hydroxides for each mole. So that's 4 molar solution of hydroxide. So 2 molar solution of calcium ions. So the hydroxide bases are pretty easy. Just dissolve them in water and you've got the hydroxide. But there's a lot of bases that don't contain hydroxide, because when they react with water, they produce hydroxide in the water by stealing a proton away from water. So bases react with water to produce hydroxide ions. And so this is in contrast to the soluble hydroxides that directly produce the strong hydroxide base. So let's look at methylamine. Methylamine is this NH2 group stuck on an organic molecule. That's an amine. And so a lot of times this word amine will tell you it's a base. And so when we put that into water, there's this lone pair of electrons on that nitrogen, and it will steal a proton away from water. And so it makes this group, this methyl ammonium, we'll write that out. Notice how the amine, this piece, became ammonium. That's a nitrogen bonded to 4 things. And when nitrogen has, it has only 5 valence electrons, it can share 3 of those. But when it donates both of those to another thing, like the proton to make a bond, then it can only, it brought, essentially lost an electron from its valence shell and makes a positive charge. And so this positive charge is divided over this whole group surrounding the nitrogen. And then when it takes a proton from water, you end up with the hydroxide base. So, methylamine doesn't have a hydroxide in it, but you put it in water and a hydroxide appears because it stole a proton from water. So that's how all of the organic bases work. You could also put an anion in water, like the acetate anion. And so if we stick the acetate anion, we have that negative charge. It would love to cancel that negative charge by grabbing a proton. So it does. It grabs a proton from water and makes acetic acid and hydroxide. You say, but wait, I thought acetic acid was an acid. Yeah, but we started with its conjugate base. We started with the acetate, and it stole a proton to make acetic acid. So acetic acid is actually a product in this case. So if you put any of those anions in water that are not like strong electrolytes, they're going to act as bases, and they're going to steal protons and make a basic solution. So let's think about a generic base. How might we generalize this? We might start with B as base, reacting with water, and it steals a proton from that water and makes HB plus. You could also write it BH plus. I think the book writes it that way, BH plus. Either way is fine. What you're just showing is that base took a proton from water and gave us hydroxide. So does everybody get the generic case? Because you'll see that all the time. It's B plus water gives HB plus or BH plus and hydroxide. That's really convenient because sometimes your basic molecules are absolutely huge. Like cocaine is an organic base. It has an amine. And who wants to draw out that whole huge structure? Or even worse, like heroin or morphine. Those are basic structures too. Really big molecules. And so it's a nice shorthand to just say, okay, here's the reaction with heroin and water. It's B plus water gives HB plus and hydroxide. So let's talk about these reactions that we're writing. You're not going to be able to go to the shelf and see this acetate ion. You're not going to be able to go to the shelf and find a bottle of anions. Okay. So what are you going to find on the shelf? Okay, you're going to find the molecule, sodium acetate. So if you wanted acetate anion, you've got to find it coupled with a cation. And so you would look for sodium acetate, or you might move down in the alphabet and find potassium acetate, and that's what you would find a bottle of. You dissolve this in water. It's a strong electrolyte. That sodium is dissolved, it completely comes off the acetate. And now you have the acetate reacting with water, making acetic acid and sodium hydroxide. Notice the sodium's in both sides, but it's really a spectator ion. But if we wanted to write everything out like molecules, that's called the molecular equation. So this is also a review from Chem 1. We had 3 types of equations. The molecular equation. Do you remember what the other one was called? I think it's probably in your notes. The complete ionic equation, where if it's soluble in water, you split it apart. And so the sodium acetate is soluble in water, and so we split that apart. So as soon as we put that in water, it forms ions. It has the acetate anion and the sodium cation. And water is fine, it's liquid. Then we have the acetic acid, which is a weak acid, so it hangs onto the proton in the molecular form. Then we have the sodium ion and the hydroxide ion. And so notice how this is the complete ionic equation. It has all the ions, but what is the ion that we really don't care about? Exactly. Sodium is a aqueous on the left, aqueous on the right, so we could cancel that out and write the net ionic equation. So all of the reactions that we're talking about in the equilibrium case are almost always the net ionic equation. It doesn't matter if it's sodium or potassium or lithium that you bought the acetate with. Those are going to be spectator ions. And so we're just really looking at the net ionic equation. And Lily, to your point, that it might be charged on both sides because it's the net ionic equation. There's a spectator ion on there that we don't really care about. So that's why we could buy, or we could show an acetate as a negative charge. Where's the positive charge? It's a spectator, and so we don't really care about it. It's like the sodium in this reaction. So we will be dealing with these net ionic equations, but I just always want to take an opportunity to review. If you're wondering, how do we buy a bottle of ions? We can't. We have to have the spectator ion that goes with it. The best spectator ions in these cases are going to be our group 1 ions like sodium or potassium. They're really cheap, and they stay in solution and they don't interact with the reaction. Now, if I want to get a molecule, let's say I have a cation that I want to do an experiment with, but it's hard to find a salt that is soluble for, say, sulfide. Sulfide is going to be insoluble. So how do I get a bottle of sulfide that when I put it in water, it dissolves? I got to put sulfide with something that is, let's see, not sulfide. Let's go with something else. Let's go with something like barium. I want a cation that I want to get into solution. There's a few things that barium will precipitate with, and I want to get barium in solution so that I can do a reaction with it. I buy it with the nitrate. So if I want a cation and I want to make sure that cation is soluble, I'll pair it with nitrate. So barium nitrate is a great compound to buy because that nitrate is a strong electrolyte. It's going to let go of the barium and it's going to go into solution. Then my barium can precipitate with stuff. Or if I want mercury or lead or any one of those metal cations that are going to precipitate with things, if I want to make sure I get them in solution, I pair them up with nitrate. Silver nitrate is really common. If I'm going to precipitate chlorides, I want to buy that silver in a way to get it in solution. So I'd buy a silver nitrate, and that would go into solution. So let's talk about the relative strengths of acids. We've talked about some strong acids and some weak acids. What makes an acid strong or weak, or how can we rank them? Well, we know these Bronsted-Lowry acids are proton donors, and the strength of an acid is measured by the extent to which it forms this hydronium ion in water. And so here's our generic reaction. Is there a number we could put to this reaction? And the answer is yes. It's that equilibrium constant expression. And so if this Ka is big, then we produce more hydronium ion. If it's small, we produce less. So the size of this Ka numerically will tell us how strong the acid is. So if you have a bigger Ka, it's a stronger acid. And so strong acids yield 100% H3O plus. You put them in water, it's all products. And so it's roughly infinity. Well, what is infinity? Well, 10 to the 14 or more. So it's going to be a really strong acid if Ka is like 10 to the positive 14 or more. Weak acids yield almost zero hydronium ion. And so Ka is almost zero because the numerator is zero. And so 10 to the minus 3 down to 10 to the minus 14, those would be really weak acids. So So we can just look at Ka and determine how strong that acid is. Water can behave like a, we'll get to water in a second. So this generic acid, again, we call this Ka value the acid ionization constant, and they give the strength of acid. So here's some sample reactions from the book, from the OpenStax book. So here's acetic acid reacting with water, giving the hydronium ion and the acetate ion, and we see that Ka is 1.8 times 10 to the minus 5. Here's nitrous acid. It's not nitric acid. This is nitrous acid. So how can I tell the difference between nitric and nitrous acid? Yeah, this is NO2, okay? HNO2 is nitrous acid. So nitrous acid is a weak acid. Nitric acid is a strong acid. Okay, and here's its Ka, 4.6 times 10 to the minus 4. So which is a stronger acid, acetic acid or nitrous acid? Nitrous acid, because it's 10 to the minus 4. So this is 0.00046. So 4.6 times 10 to the minus 4. This one is 0.00018. You see, this is a larger number by like 40 times larger. Okay. And then here's the hydrogen sulfate ion, and it's a weak acid, 1.2 times 10 to the minus 2, so it's 0.012. So it's a stronger acid than the other two. So you can compare those Kas, get comfortable looking at the exponents. So 10 to the minus 2 is larger than 10 to the minus 5. Okay. That's a thing that really trips some people up. They just don't really get these powers of 10. Okay. So if you need to work on that, then please do. If it helps to write them out, like I just did here, then you get comfortable with it. You can say, yeah, this is 1.2 times 10 to the minus 2, 4.6 times 10 to the minus 4, and 1.8 times 10 to the minus 5. You can see how much smaller those numbers get. We deal with some really small numbers in this region. Some of these acid constants are 10 to the minus 10, 10 to the minus 12. So you got, 11 zeros and then the number. So they're really, really small. We'll deal with the problem with this percent ionization in a later part of the notes. But that's another way you could measure the strength of an acid, is to calculate the percent ionization. So how much hydronium ion is produced per unit of acid. Let's look at the relative strengths of bases. So bases accept protons. They really work with water to take that proton away and make hydroxide ion. And so then we could look at this generic reaction and calculate the Kb. So this Kb would be the base ionization constant. Strong bases yield 100% hydroxide ion, so Kb would be huge. A weak bases yield almost none. So again, Kb could be 10 to the minus 3 or 10 to the minus 14. Something in that range. I mean, it could be all the way up to 1, but I'm talking about the really small ones. Let's compare some base reactions. Okay, so here's our generic reaction and our Kb, and here's the nitrous acid. The nitrous acid produces what anion? What would we call this one? It's not nitrate. What is the one that's got less oxygen than nitrate? Nitrite, right. The naming really becomes important in this part of the course, because what if you come across a problem and it says a 10th molar solution of sodium nitrite? You're like, oh heck, what is that? Right? So you got to know what ITE means. It's not ATE. And so if you memorize nitrate, just knock off an oxygen and you've got nitrite. Okay. What is sulfate? SO4. What do you think sulfite is? SO3. Yeah. Chlorate. That one's a little tricky. ClO3. What do you think chloride is? ClO2, yeah. If you go less than that, you get into hypo. So hypochlorate has ClO. It's just one oxygen. All right, so we get up back to chlorate. If I've got chlorate memorized, that's ClO3. What if I add more? I've got to go up, like hyper, but you just use the per. Okay, it's perchlorate, it has 4. So that series tells you all of them. If you can remember chlorate, it has ClO3. Perchlorate is more. Chlorite is down to 2. Hypo is even less. ClO1 or ClO. So if you put that in water, it steals a proton, produces hydroxide, and here, look at this base, Kb, or base ionization constant. It's really small, 10 to the minus 11. So yeah, I'm going to do it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2, 1, 7. Okay, and that's going to be a lot smaller than the 10 to the minus 10 or even 10 to the minus 5. Okay, this one is the acetate anion. Couple that with water, you make acetic acid, and here's the base constant for that. So 5.6 times 10 to the minus 10. Here's ammonia. If I bubble ammonia in water, it'll dissolve in water. It will steal a proton and make ammonium ion. Ammonium cation. Okay. So that one you have to memorize that. Ammonia and ammonium, those two are so common. I want you to know those because I don't want to just think, you know, I'm writing out the problems, I'm typing. I just assume you know what ammonia is. So meet me there. Know what ammonia is. And I'm typing out ammonium's, you know, ammonium sulfate, and I type that into a problem and I use text. I don't draw out the thing because I expect you to know what ammonium is. So definitely know that because it's so common. And that one is, again, the base constant for ammonia is 1.8 times 10 to the minus 5. Kind of coincidental that that's the same as the acetic acid, Ka. It's just coincidence, okay. And then you can calculate the base ionization again. You take, if you know the initial concentration of base and you calculate how much hydroxide was produced, that's the percent ionization for the base. So let's do some problems with these, okay. So water by itself, we'll get to the problems in a sec. Water by itself will act as an acid and a base. And so if, you know, if this water acts as a base and this one is an acid, it donates a proton to the base and we end up with hydronium ion and hydroxide ion. So this is called the auto-ionization because it's water by itself and then we produce ions out of the blue. All of a sudden we have hydronium ion and hydroxide ion. And so it's called water auto-ionization, and we have this auto-ionization constant, which if you look up here, there's it's just the products because those are the only things that are aqueous. Okay. So notice that no liquid water shows up in the equilibrium constant expressions. And so this one's products over reactants, but there are no reactants that can change concentration. It's water and water. So that's going to be a fixed molarity. So we just lump that into the constant. We only have in the equilibrium constant expression the concentrations that can change. So only the aqueous species show up. And when you take this small amount of hydronium ion and a small amount of hydroxide ion that shows up in pure water and multiply them by each other, you get this constant, 1 times 10 to the minus 14. So that you definitely got to know that number. So memorize this. And this one will be one that you memorize by just use. I mean, you're going to use it so often. And you may know some of the parts of this. I mean, when we get to pH, it'll definitely sort of click with you that the pH and the pOH add up to 14. This is where that comes from. Okay. So how acid-base equilibria and water interact. You know, we have this acid interacting with water to make hydronium ion and the acid anion. So here's the Ka. And we have this base interacting with water to produce the acid and hydroxide. What if I were to were to add these two reactions together. So then I have all four of these species added together, and they produce all four of these species. But notice on either side I have some identical things. And so the acid on either side would cancel if I add these two reactions, and the anions on either side would cancel. And when I add these together, I end up with this reaction. I end up with two waters on the left, the hydronium ion on the right, and the hydroxide ion on the right. And I end up with the equilibrium constant for water, for the autoionization of water. And so what this means is that water is governing this interaction of acids and bases. Because perhaps you thought if I dissolve this acid in water and it produces the anion, that anion could steal a proton back, and it does. It makes the acid. And so there's going to be an equilibrium between both of these reactions that's really governed by water. So if one of these goes up, the other has to go down. This also means that if I look at these two reaction equilibrium constant expressions and I multiply them by each other, because that's what you do when you add reactions, is you multiply their equilibrium constants. The A minus cancels and the HA cancels, and I'm left with hydronium ion and hydroxide ion. So we have this equation here, which is really useful. So memorize this and memorize this. Sometimes they'll tell me that we've got this base molecule that's dissolved in water, but they'll report the Ka value. But I've got a basic reaction and I've got the Ka. I need the Kb. And so I've got to use this bottom equation to get to Kb. All right, so how can I do that? Well, they're giving me the Ka, and I know by memory Kw. So I know how to get Kb. If I've been given Ka and I know Kw, then I can calculate Kb. So let's look at how these ratios of hydronium and hydroxide ion are balanced by water. So here's our reaction. Here's the water equilibrium constant. And it's like a seesaw. I don't know if you guys still have these in your playgrounds when you grew up, but we always had them. Ours did not have the little tire bumper on the bottom. You'd about break your back if someone jumped off. And it was at the ballpark, and you know, your friend would say, "Hey, you want a seesaw?" And I would say, "What?" Sure. No, I say no offs. And they say no offs. Promise? Yeah. You know what I mean by no offs?
Don't get off.
Yeah, you're seesawing and they get you up there and they jump off and you go slam down. Yeah, and so you kind of had to trust each other. And if your buddy, you know, got you, and then you wouldn't seesaw with him anymore. Right? Now, real trust was at our ballpark. They had a mulberry tree right by the seesaw, and all the low berries had been picked off already. And so if you had a friend you could really trust, you could seesaw and they'd lift you up and you would pick the mulberries off the tree standing on the seesaw. Extreme trust. But you had something on them, then you could share the berries with them. But if they dropped you on your head, then you wouldn't share the berries. So that was always fun from my childhood. Good fan of seesaws. But let's think about the concentrations. And so this is always a balance between the hydronium and the hydroxide ion concentration that's governed by Kw. So if one goes up, the other has to go down because their product is a constant. So Kw is equal to the hydronium ion concentration times the hydroxide. So if one of those numbers goes up, the other has to go down, and vice versa. So that's how pH and pOH or hydronium ion and hydroxide ion concentrations are coupled with each other. And the range is dramatic. It goes up, you know, from 1 down to 10 to the minus 14. And so I've got this little measurement here on my seesaw. It looks like my hydroxide ion comes in at 10 to the minus 3, and my hydronium ion comes in at 10 to the minus 11. And so if you multiply those together, you get 10 to the minus 14. And so those exponents add up to 14. And so if it was 10 to the minus 4, the other would have to be 10 to the minus 10. If it was 10 to the minus 6, the other would have to be 10 to the minus 8. And if it was equal, they'd both be 10 to the minus 7. And so that would be a neutral solution where they're perfectly balanced in the same number. It would both be 10 to the minus 7 because their product has to equal Kw. So here's some acids and their conjugate bases and the different strengths. So these are some nice representative molecules, different acids. So like here's the let's see, the chlorous acid. Yeah, I got to make sure I got my naming right. So this is chlorous acid and the chlorite ion. Chlorous acid and chlorite ion. So let me go ahead and write those out just because I struggled with it. I want to write it out for you. So us becomes ite. Okay, and it's 10 to the minus 2 and 10 to the minus 12. That's Ka and Kb. You multiply those together, you get Kw. Okay, and here's the hydrogen fluoride acid or hydrofluoric acid, and here's the fluoride of the fluoride ion. Here's carbonic acid, and here's the hydrogen carbonate ion. Again, 10 to the minus 6 times 10 to the minus 8, you're going to get 10 to the minus 14. Here's ammonium and ammonia. Here's, again, these are all within the range of water. So here's the Ka for H3O plus and for water. So this would be 10 to the minus 0 and 10 to the minus 14. You multiply those together, you get 10 to the minus 14.
Is this something we just got to memorize?
What's that?
Is this something we just got to memorize?
No, I don't really want you to memorize all of these. I will have you memorize acetic acid just because it's a nice, it's 1 point. That doesn't seem. Let's see this Ka doesn't seem right. Like there might be a mistake in the book. It's 1.8 times 10 to the minus 5. So why is it showing up at 10 to the minus 8? Doesn't make sense. So I'm going to put a question mark on this guy right here. I don't think that's right. Okay. Here's the same kind of table, but without the numbers. And it just has lots of different names of acids in there, anions, and so on. And this is nice because it helps you with the naming, right? Here's hydrogen sulfide. Here's the hydrogen sulfide ion. Here's the carbonic acid and the hydrogen carbonate ion. Hydrogen cyanide and cyanide ion. So this is great stuff. Okay. So let's now add together this ice table business and the hydroxide ion concentration. So here's a typical problem that you would come across. So what's the concentration of hydronium ion and hydroxide ion in 1 molar acetic acid solution? And so I want to introduce a new term. I don't believe this is anywhere in your book, but it's the terminology that's really helpful. And it's called the nominal concentration. What does the word nominal mean? Just think of a name, right? And so this is what's on the outside of the bottle. So you can look at the outside of the bottle and it'll be 1 molar acetic acid. So that's CHA, just concentration of acetic acid. It's not at equilibrium, but that's what you've written on the bottle. Okay, that's how you made it up. Okay, so naturally we have 100 or 1 molar minus X plus X plus X. We have Ka. So we write this out, the hydronium ion concentration, the acetate ion over the parent acid, and water is nowhere to be found in that one. We can combine these with the X's. So we have X squared over 1 minus X. We're headed straight for that quadratic formula. But this guy right here, we could assume is small. This minus X is small. And so here now we can put some criteria on this. For the acid-base equilibria, it's just really nice to have such small numbers. If CHA is greater than Ka, is over Ka is greater than 100, then this is a good assumption. So now I can kind of give you a criterion for when to make this assumption, if you're going to want to avoid that that quadratic formula. If this was less than 100, you probably better do the quadratic formula or swing it all the way to the right and come back. So we're going to simplify that equation, and we have just X squared over 1 equals Ka. And so if we solve for x, then and this is equal to 1.8 times 10 to the minus 5. So that's the Ka for acetic acid. So if we solve for x, that is the hydronium ion concentration. And it's 0.0042. So now that we know x, we can compare that to 1 and we can check. So yeah, 1 minus 0.0042 is essentially 1, right? It's a really small number. So that's a good assumption. Any questions about it to this point? I think the acid part of equilibrium is easier than just the generic equilibrium, where you have, all kinds of crazy coefficients. All the time, these coefficients in front of the acid equations are all 1. So you don't have a 2x, you don't have a 3x, you don't have anything cubed or anything like that. So I really enjoy the acid-base equilibrium problems because they're much easier than the others. I just gave that to you. Yeah, so this was given. It should have been written in the problem up here, but it wasn't. Okay. If it wasn't in the problem, let's say you just came across this and you wanted to do this on your own, you'd have to look it up. And so you'd have to go on the internet and say, what's the acid dissociation constant for acetic acid? And you'll find it. Most of the time, you've probably been scared away from Wikipedia. But for science, it's pretty good because if you look to see where they're citing their work, they're getting it from the CRC. CRC is much more reliable. They're pulling those numbers from the CRC and putting them in Wikipedia, so it's faster. But if you want to just check your work and make sure you're not getting fooled, you can go to the NGL library, go to research guides, science, chemistry databases, and find the chemical rubber handbook, or CRC handbook of chemistry and physics. And it has all of the acid dissociation constants and everything in it. So yeah, our assumption checks out. Now, how much hydroxide ion do we have? Well, here's the Kw, and if I know this concentration here, this goes in here, and I can solve for the hydroxide. So the hydroxide is Kw over the hydronium ion concentration, so it's 2.4 times 10 to the minus 12. So even though I solved an acid problem, I can calculate the hydroxide concentration using Kw. So it really doesn't matter which I solve. I could solve a base problem, and I could get to the hydronium the same way. Okay, this is what's the percent ionization of this 1 molar acetic acid solution. So this is just using the results from the previous problem, and then this definition of the percent ionization. It's how much acid you started with. That's the whole. Remember, percentages are part over whole. The part is the part that made the hydronium ion concentration. The whole is what you started with. And so it's just 0.0042 divided by 1 times 100%, or 0.42%. Okay. So not very ionized. So it's definitely a weak acid. You see how it doesn't produce a lot of hydronium ion. Okay. So there's a lot of practice problems. We can do these if we ever run out of time on any of the future notes. But that's all you have in your notes, and I'll see you next time. All right.
Sorry for coming a little